In this video, we're going to be covering how to quantitatively determine the free energy associated or conserved in an electrochemical or proton gradient. And then from there, I want to use this information to help explain how ATP synthesis works and specifically investigate the thermodynamics involved with ATP synthesis. So we can mathematically express an equation that determines the free energy associated with an electrochemical gradient of an ion. So before we get into these specific details right here, let's just review the function of the electrochemical gradient. So remember that the electrochemical gradient is the main factor that's responsible for producing ATP, and the electrochemical gradient is comprised of two factors. The first factor is the chemical potential, which is just the concentration of hydrogen protons of the matrix relative to the hydrogen concentration of the intermembrane space. Okay? And we remember that the intermembrane space has a very high concentration of protons and therefore very acidic or characterized of a low pH. And then the matrix has a very low concentration of hydrogen protons and therefore a very high pH. And thus we refer to this chemical environment to be alkaline, right? And then the second factor of the electrochemical gradient is the electrical potential, right? Which just refers to the charge distribution between the matrix and the intermembrane space. So if we take a look here, right, we remember here that this is the inner membrane of the mitochondria, the IMM. This is the intermembrane space, the IMS, and then this is the matrix. We can see here that the charge distribution here is relatively positive, and then on the matrix side we observe it to be relatively negative or less positive, right? So that's just what the electrical potential is referring to. It's just the charge distribution between the matrix and the IMS, right? So going back to explaining going back to explaining how we can quantitatively determine the free energy change associated or conserved in an electrochemical or proton gradient. So remember that the free energy is just the amount of an exact number or an exact quantity of how much potential energy is associated with the system. In this case, we're looking at the chemical energy associated with the electrochemical gradient. Okay? That's essentially what we're just investigating here. Okay. So we see here that delta G of the electrochemical gradient is comprised of two factors here. Remember the two factors, the chemical potential and then this is the electrical potential. So we saw here two factors. Now we're seeing them in mathematical expressions. We see that the chemical potential is comprised of the gas constant, which is just 8.3145 joules per mole per Kelvin. It's also comprised of the temperature, and then a natural logarithmic expression of a ratio of concentrations. So we can see the relative ion concentrations in two regions, where the second concentration is always greater than the first concentration. So if we were to take a look here, we can see here that the natural logarithm of the concentrations can be expressed like this. So remember if we wanted to find the concentration of hydrogen protons, all we need to do is algebraically solve for the hydrogen concentration by using this formula here. Remember that the pH is equivalent to the negative logarithm of the hydrogen ion concentration. Well, to solve for the hydrogen ion concentration, we just simply impose a power to cancel out this operation right here, right? Because 10 to the power of negative pH is equivalent to the hydrogen ion concentration. So that's essentially what we're doing here with this formula right here. So 2.3 times the concentration or the pH of the matrix minus the pH of the intermembrane space is equivalent to the change in pH, as I show here in this diagram. Alright? So that's essentially what so this formula here, this mathematical expression, essentially comprises the chemical potential for the change in the energy of the electrochemical gradient. Now for the electrical potential, for the mathematical expression for the electrical potential, we see that there is the absolute value of an electrical charge of an ion, which is represented by Z. We see that for hydrogen ion protons, it's +1, given that when a hydrogen ion forms, it only has a charge of +1. Now, the Faraday's constant, F, just refers to the magnitude of the electric charge per mole of electrons, which in this case is 96,500 coulombs per mole. Okay, and then the last part of the mathematical expression for the electrical potential is the transmembrane difference, represented by this symbol here. Transmembrane difference in electrical potential in volts. So this just refers to the transmembrane difference in electrical potential in volts between the two sides of the membrane. So if the destination compartment is more positive than the initial compartment, the way the transmembrane difference is a positive value, and in essence, it states that it implies that the hydrogen ions are pumped from the matrix to the intermembrane space. However, if the destination compartment is more negative than the initial compartment, then the transmembrane difference is a negative value, and the hydrogen ions flow from the IMS to the matrix. So let me just try to break this down a little more. So essentially what this formula does here, or what this factor represents, is the flow of protons. It determines the direction of the flow of protons. Not determines, but rather implies. Okay. So essentially what we're left with is a change in pH, which is equivalent to, so just to clarify, for the electrochemical gradient, the change in pH and the change in the transmembrane difference usually takes on two values. and these two values are 0.75 and 0.15 to 0.20. So let's keep the mathematical expression of the electrical chemical potential in mind as we move along, as I move forward to explaining how ATP synthesis works. Let's take a look at the concept of the free energy associated with, or the potential free energy associated with transporting a hydrogen ion with or against its concentration gradient. So this is called delta G transport. Now delta G transport, as I just said, is the potential free energy, or the potential or free energy associated with transporting a hydrogen proton with or against its concentration gradient. And these are just all the values that I showed, that I represented here before. R is just the gas constant, T is just the temperature, which is just represented in Kelvin, which is 298 Kelvin. So R times T gets you 2,478 joules. C2 is just the concentration of the destination compartment. C2 is the concentration of the destination compartment, and C1 is the concentration of the initial compartment. Z is just the charge of the electrical ion, charge of an ion, which in this case is hydrogen, and has a charge of +1, so therefore Z equals +1. Faraday's constant is just 96,500 coulombs per mole, and then the transmembrane difference in electrical potential is typically plus or minus 16 volts, depending on the direction of the flow of protons. So if it's moving from a place of greater positivity to greater negativity, then we consider the change to be negative. Or no. If the destination compartment is more positive than the initial, then the wavelength is a positive value, and then vice versa. If the destination compartment is more negative than the initial, then the wavelength, the change is negative. Yeah, so yeah, exactly as how I said it. So let's say, for example, we want to look at a hydrogen proton that's going with the flow of its concentration gradient. So H proton flows from high to low concentration. In this case, we would refer this as the IMS, and this is the matrix. So we need to make note of the the transport direction across the membrane. So we see here that the concentration of hydrogen protons in the IMS is greater than the hydrogen concentration in the matrix. So in this case, C1 is greater than C2. We determine C1, C2, and the sign of the wavelength function, or the transmembrane difference. So we see here that C2 is the concentration of hydrogen protons in the matrix, which is 10 to the -7 right here. We see here that the concentration of the IMS is 10 to the -6. So we see that because hydrogen ion concentrations, or the hydrogen ion concentration, flows from an area of high positivity to low positivity in terms of charge, we see here that the transmembrane difference is from positive to negative. So we see that we should apply a negative value here, negative 0.16 volts. So we then plug in all the values that we already know. 2,478 joules per mole times the natural logarithm of 10 to the -7 over 10 to the -6. plus the positive charge plus times the Faraday's constant times negative 0.16 volts, and then we sum up to negative 21.1 kilojoules per mole. So as a conclusion, we find that negative 21.1 kilojoules per mole is released as 1 mole of hydrogen ion flows back into the matrix from the IMS. Okay, so in essence, we see here that as a hydrogen ion flows from an area of high concentration to low concentration. So high concentration, low concentration. We see that negative 21.1 kilojoules per mole is released when this reaction occurs. Okay. Now, if we take a look at the hydrogen ion flows from low to high, or if we take a look where a hydrogen ion concentration flows against its concentration gradient, so from low to high concentration, we say that this hydrogen ion is going against, or the flow of this hydrogen ion concentration is going, this hydrogen ion is going from low to high concentration, and therefore it's going against its electrochemical gradient. So make note of the hydrogen transport direction across the membrane. So if we see here, the pH of the IMS is 6. Therefore, the concentration of the IMS, the hydrogen ion concentration of the IMS is 10 to the negative 6. Conversely, the matrix has a pH of 7. Therefore, the concentration of the hydrogen ions will have a pH of 10 to the negative 7. Okay. Determine C1, so we need to determine C1, C2, and sign a CV. So C2 has an ion concentration of 10 to the negative 6, and C1 has an ion concentration of 10 to the negative 7. Okay. So, and we see that the wavelength function here has a positive value because we want to observe that we're observing that the hydrogen ion is going from an area of less positivity to greater positivity, or from a negative from a relatively negative space into a positive space. So the transmembrane difference is 10 plus 0.16 volts. Same thing as before, we apply those same values, and we see that the value is that the free energy associated with the transport of an ion, delta G transport, equals 21.1 kilojoules. Which is essentially the exact same figure as what we saw earlier, except this time it has a positive sign here, right? So we see here that it will instead take 21.4 or 21.1 kilojoules to pump 1 mole of hydrogen protons into the IMS from the matrix. Right, because the IMS is relatively positive compared to the matrix. An idea of how to quantify the energy associated with the electrochemical gradient, and now that we're aware of its two factors, which is the chemical potential and the electrical potential. We understand that there's a natural flow of ions moving from the IMS to the matrix, right? So H protons are usually moving through ATP synthase and in doing so releasing a specific amount of energy. So, and allowing these ions to flow according to their gradients, in essence reaching equilibrium, energy is released, which is represented by delta G, and the free energy that's released from these reactions can be used to do work, and that's essentially how ATP synthase works. ATP synthase is an enzyme complex that facilitates the diffusion of hydrogen protons back into the matrix, and it can utilize the energy generated from this phenomenon to synthesize ATP. So let's break down the structural components of ATP synthase. So ATP synthase is what we would call an F-type ATPase, where it is a multi-subunit protein comprised of two key components. So the first component is a transmembrane pore, denoted as F0, and we can see that here in this diagram right here. F0 is a transmembrane pore protein. And then we see that it also contains an ATP binding peripheral membrane unit. So peripheral meaning it's in the periphery, or it's attached to F0, right? And it binds ATP. Now the key functions of ATPase are to transport protons using energy derived from ATP hydrolysis, but that's in its reverse function as an ATPase, right? ATPase can also function as an ATP synthase, and ATP synthase would catalyze the transport of hydrogen protons in the opposite direction, right? And when this happens, when it catalyzes transport of hydrogen protons in the opposite direction, so going from the IMS to the matrix, so going down its concentration gradient, hydrogen protons flow down their concentration gradient and they release energy. So ATP can then be synthesized, and that's what the primary purpose of the F0 subunit is, or the sorry, not the F0 subunit, the F1 subunit is. It's the peripheral membrane protein that synthesizes ATP from the energy released from exergonic flow of protons back into the matrix from the intermembrane, from the IMS, not the IMM. That's the inner membrane of the mitochondria. So the key function of FU, so just to summarize, ATP synthase breaks down into two subunits, F0 and F1. F0 transports F0 transports hydrogen protons. F1 synthesizes ATP. Okay? That's essentially the basic idea behind ATP synthase. This is one of the last concepts for ATP synthesis. So now that we have an idea of how ATP synthase works, and now that we have an idea of how the electrical chemical gradient can be used to do work, we can now go into the idea of the P P.O ratio, which just refers to the number of moles of ATP formed for every half of O2 reduced, or for every 2 electrons passed to O2. So remember that NADH one molecule or 1 mole of NADH pumps 10 protons in total, 4 from complex 1, 4 from complex 3, and 2 from complex 4, right? By experimental determination, we find that the widely accepted value for the hydrogen protons required to synthesize ATP is 4. So out of those 4 protons, 3 of those protons are used for the direct synthesis of ATP via exergonic flow to release energy, to release potential energy. Okay. So remember that delta G transport is just the potential and free energy associated with transporting a hydrogen proton with or against its concentration gradient, right? And we made these calculations already, where 21.1 kilojoules per mole is released as 1 mole of hydrogen protons flow back into the matrix from the IMS, right? But before we can go into the exact specifics of how ATP is synthesized, we should first look at the thermodynamics associated with ATP synthesis. So remember that ATP hydrolysis releases energy, right? So by experimental calculations, we see here that delta G, or delta G1 subscript, is equivalent to negative 45 kilojoules per mole. That's the amount of energy associated with ATP hydrolysis. These are the relative, not the relative. These are the calculations I performed to get this value. So we see here, remember that delta G1 is equivalent to negative RT ln KEQ over Q cell, and we have to assume that Q cell is under 80. We have to assume these conditions where the concentrations of the where we assume the general concentrations of the substituents of the reaction, where the concentration of ATP is equivalent to 5 times 10 to the negative 3 molar concentration. ADP has a molar concentration of 1.5 times 10 to the negative 3, and the inorganic phosphate has a concentration of 10 times 10 to the negative 3, right? So we can see here that, remember that Q cell is equivalent to the concentration of the products over the concentration of the reactants. We apply this is just the concentration of ADP times the concentration of inorganic phosphate, because we're doing ATP hydrolysis, right? So these are the products, and then this is the concentration of ATP, which is just the reactant. Okay. And then by plugging these values in, we get a value that is equivalent to 3 times 10 to the negative 2. So that's the reaction quotient. We see here that the equilibrium constant is 2.2 times 10 to the negative 5, 10 to the 5. So we see here that by plugging all these values in, negative RT, which is just negative 2,478 joules per mole, times the natural logarithm of the of 2.2 times 10 to the 5 over 3 times 10 to the negative 3 gets us negative 44,877 joules per mole, which is just approximately equivalent to negative 45 kilojoules. So that's just the amount of energy associated with ATP hydrolysis. But if we wanted to find the amount of energy associated with ATP synthesis, ATP synthesis requires energy, right? Now we take a look at the relative concentrations again, and this time we see that it's the concentration of ATP over the concentration of ADP plus PI, because we're going in the reverse direction. So instead of performing ATP hydrolysis, we're performing ATP synthesis. So this is ATP hydrolysis. This is ATP synthesis. ADP plus PI gets you ATP. You know what? Just to make it easier. There we go. So we see here that we determine Q cell to be 333.33, right? Now, the KQ for ATP synthesis, KQ for ATP synth, or ATP synthesis, is equivalent to KEQ, the inverse of ATP hydrolysis, right? Or 1 over KEQ ATP hydrolysis. Whoa. Okay. So with ATP hydrolysis, with ATP synthesis, we find that with the equilibrium constant 1 over the equilibrium constant of ATP hydrolysis, we determine this value to be 4.54 times 10 to the negative 6. Okay. Therefore, the energy associated with ATP synthesis is equivalent to negative RT ln KQ over Q cell, negative 2,478 joules per mole times 4.54 times 10 to the negative 6 over 333. We experimentally determined that value to be 44.6 kilojoules per mole, which is just approximately 45 kilojoules per mole. Okay, so we see here that this value is the exact opposite of ATP synthesis, right? And that's how we determine how much energy is necessary to synthesize 1 ATP. Exactly approximately 45 kilojoules per mole of ATP. Now, we see here that 21.1 kilojoules per mole of 21.1 kilojoules per mole is released as 1 mole of hydrogen proton flows back into the matrix from the IMS. So, based on the math that we've observed here, we observe that 3 hydrogen protons must flow into the matrix, since 3 times 21.1 kilojoules per mole is 63.3 kilojoules per mole, which is greater than 45 kilojoules. So it has to be at least 40. So to synthesize 1 ATP, we have to have at least 45 kilojoules of energy worth of 45 kilojoules of potential energy to synthesize 1 ATP. Now, 1 hydrogen proton is used in the phosphate translocase transporter, where it hexagonically flows into the matrix to allow active transport of the inorganic phosphate into the matrix. So let me explain this. So the electrochemical gradient or proton motive force can actually be used for other functions as well, besides synthesizing ATP, including facilitating the transport of other molecules aside from hydrogen protons. So, or aside from the hexagonic flow of hydrogen protons. So, let's explain here. Let's take a look at adenine nucleotide translocase. So, translocase refers to the transport of a molecule, right? And in this case, what's being transported is an adenine nucleotide. Okay. Now, this protein acts as an antiport or a co-transporter, where it refers to the transport of two molecules in opposite directions. So it transports ADP into the matrix, which is an unfavorable reaction since the matrix is negatively charged, and ATP has a charge of -3. Therefore, energy is required, and therefore we rely on the hexagonic flow of ATP into the IMS, which allows ADP to flow from the IMS into the matrix. So we see here that ATP is flowing into the IMS, which is favorable because the IMS is hugely positive, right? IMS hugely positive. So it's favorable for this reaction to occur. But the energy that's released from ATP flowing into the IMS is used to allow for the endergonic flow of ADP into the matrix from the IMS. Right? So essentially, that's the function of the adenine nucleotide translocase. It just transports synthesized ATP into the IMS to allow the transport of ADP, the unfavorable flow of ADP into the matrix. Okay. Now, phosphate translocase just refers to the transport of phosphate from the IMS into the matrix. Now, remember, it's for the phosphate translocase works similarly to adenine nucleotide translocase in a similar manner, where the transportation of inorganic phosphates is unfavorable since the matrix is negatively charged, and the inorganic phosphate is also charged. But this is a very necessary step, as the inorganic phosphate is a co-substrate with ADP to form ATP. So energy is required, right? So thus we rely on the hexagonic flow of a hydrogen proton from ATP synthase in phosphate translocase to allow this to occur, right? So remember here when I said that there were four protons required to synthesize ATP, 3 of those protons flowed from the ATP synthase, the FO subunit specifically, right? The other proton is from the phosphate translocase, right? Because that phosphate group will be used to synthesize ATP, so it's a bit of a cyclical nature. It's a bit of a cyclical nature that we're seeing here, right? One phosphate group goes through, right? 3 hydrogen protons go through ATP synthase, while 1 goes through translocase, the phosphate translocase protein. And essentially, that phosphate group will go react with ADP to form ATP, right? That's essentially this whole diagram here. That's the connection between the three enzymes. Now, there is no net flow of charge, or net flow of charge equals 0 during symport of hydrogen of the inorganic phosphate and hydrogen protons. Okay. So essentially, what I just described here is just a bunch of information that somehow all connects together if you think about it. 21 kilojoules is released per hydrogen proton that flows back into the matrix. Therefore, 3 protons are required to synthesize 1 mole of ATP. And to get the inorganic phosphate group that synthesizes that reacts with adenine dinucleotide adenine diphosphate, right? We need that inorganic phosphate to be transported into the matrix, and that happens through the phosphate translocase symporter, right? So I just want to direct our attention to the last overall idea here. So we want to take a look at several P.O ratios. So remember that there are 4 protons required to synthesize 1 ATP. That's the key idea here. 4 protons per 1 ATP synthesize. Right? So if we take a look at the P.O ratios of several molecules, we can say, for example, take a look at NADH. NADH donates its electrons to complex 1 and complex 3 and complex 4, right? Or sorry, the electron transport chain complex the electron donor donates to, so NADH will donate its electrons to complex 1 in the form of a hydrogen ion. 2 electrons are donated at a time, and the number of protons pumped from the matrix to the IMS are 10 protons for NADH, right? There's 10 H protons, 4 from complex 1, 4 from complex 3, and 2 from complex 4. That gets you a P.O ratio of 2.5 ATP, or 10 protons pumped into the matrix. And because there's 4 protons required to synthesize 1 ATP per ATP, we see that 2.5 ATP is produced. 2.5 ATP molecules are produced from NADH. So we see that the P.O ratio is 2.5 to 1. Okay. Now succinate, or FADH2, yeah, so remember how I said that FADH primarily represents the electrons being passed from complex 2. So there's 2 different P.O ratios for FAD. So FAD transfers its electrons as hydrogen atoms to complex 2A with succinate. Okay, this is with succinate. And 6 of those protons are pumped, right? 4 from complex 3 and 2 from complex 4. We get a P.O ratio of 1.5 ATP, so 1.5. The same thing with complex 2B. So remember that, if I remember correctly, let's see here. From complex 2B, we see that NADH is oxidized to reduce dihydroxyacetone phosphate into L3P, and then L3P will be oxidized to reduce FAD to get FADH2. This is complex. This is just the mechanism of complex 2B. And then we see that the same phenomenon occurs here. 6 protons are pumped from both complex 3 and complex 4. 4 from complex 3, 2 from complex 4. And then we see that the same P.O ratio is produced here. So succinate has a P.O ratio of 1.5 to 1 for complex when it's associated with complex 2A, and then it's associated with the same ratio with complex 2B. And that's essentially the basic premise behind P.O ratios.